Alright guys, welcome in. So we're going to jump right to it, and we're going to start off with 3.2 number 16. I do want you to keep in mind now that what we're doing now is we're at this phase in the learning, is we're taking this limit, and I mentioned this in both videos from last time, and I've mentioned it a few times before. We're taking this limit in particular, and we're now going to apply this limit to, polynomial functions, and so on. We're going to apply it to the square root of x function. We're going to apply it to the sine and other trig functions. We're going to apply it to the natural log function, and so on. So we're going to take the limit of the difference quotient. And remember, the limit of the slope equation, because all this is the slope equation, is takes the slope equation gives you an approximation, right? Like if I cross through this parabola, that's an approximation of the slope right down here. But if I want to get the exact slope there, it's more like this. So using an arbitrary set of points x and f of x, and x plus h and f of x plus h. I'll zoom in here in just a second. Thus, picking those arbitrary points, we just do y sub 2 minus y sub 1, x sub 2 minus x sub 1, we get this guy. So, and that takes our cutting line, our secant, and the line created by those 2 points would be the cutting line or the secant, and it gives us the slope at this instant as its output of this. That's what the output of this is, evaluated at a point. So you saw when we put in a value for the second one, we could flush things out, simplify, and we could get out an answer. When we evaluated, when we had put in points for x. What we're going to do now is we're going to leave this, okay? We're going to leave it in function notation. And by leaving it in this function notation and applying it to these guys, we're going to develop what are called the derivative rules. And the rules that we use for various families of functions. So instead of putting each problem that you get within all of these families into this rule, you're going to use this rule with the parent functions of these to develop some new rules. We're also going to develop some fundamental arithmetic rules for derivatives. So we're going to develop things like the product rule, the power rule would be different with the quotient rule, okay, and so on. Product and quotient are arithmetic rule properties, and we'll also do those. So anyways, just trying to give you some extra information here in addition to just getting the work done. So as you need, so keep an eye on the big picture here. We did all those different types of limits. Now we're taking this one in particular, which that part inside is how we represent the slope of this particular secant line from here to here. If we extend it, it looks like this. If we take the limit of as h, the distance h, right there, goes to 0, as this collapses this way and becomes nothing, then we're getting the slope at this instant, and we can create what's called a tangent line with that slope. We don't have to, and what we get out is just the slope. But again, if we keep this in function notation, and we think of logically what some rules might reasonably be for doing products of functions, and we think of, and we apply this to these to see what we get, then we can come up with a set of rules that we can follow so that we don't have to use this lengthy, cumbersome thing every individual problem we get. And again, why do we want this? Because we don't know. We didn't know at the early stages of the calculus how the slopes change along a curve where the slopes visually change, as you can see. Each of those has a different slope, and they're all close to what I drew them next to at that instant. Okay, so with this all said, we're now going to swivel over to 16 and dive back into the arithmetic of the chapter. Okay, and what 16 is asking us to do is to match the graphs of a and d derivative function with possible graphs a and d of the corresponding functions. So to do that, we need to consider a little bit about what derivatives represent and how we can see those representations on the graphs. So let's do that right now. All right, so let's go ahead, and what we're going to do is start with the bottom part of the graph down here, and we're going to look at this blue line here, blue line, big A, and we're going to say to ourselves, what's the slope of this line? And we can see it is, it appears to go, let me count it out and then unpause the video. Okay, so I'm gonna show you two ways to do this. I have it all figured out. Like I said, I was pausing the video real quick there. The two ways you do these visual matchings are you can quickly approximate the slope. That's one thing you can do visually looking at them. But you can also use what I call the increasing or decreasing elimination method. So, first of all, you have to remind yourselves, what is a derivative? What does a derivative mean? Remember, derivative is means either the function for f prime of x, or what f prime of x represents, which is the slope of f of x. So you're going to develop a new function. So you're going to have some stuff over here, like some x's. I'm not even going to write it in. You're just going to have a new function over here, okay, for different things. But what that all equals when you put in values of x is a slope value. F prime of x are slope values. These are slopes, and they're the slopes of the function f of x that you developed by doing this equation. Okay, so what that means is, when we're looking down here, this graph up here at the top are the derivatives. So the top graph, okay, so I'm going to make, like, there's the top graph over here, and then there's this graph down here. The top graph is a graph of slopes. The bottom graph, which are f prime of x. So f prime of x is this guy up here, which is what we get when we do the difference quotient for these guys. And f of x is what's down here. And this is just the original function value and how that plot looks, the original function, nothing more. So we're going to start with the original function, and there's two things I notice about graph A. First, that it's increasing along with C. And increasing means positive slope, and we see only two lines here that are above the x-axis. So what we want to start building for ourselves, if you're new to this, is you want to start building some patterns. So when you think of derivatives, above, if it's f prime, okay, and you're above the x-axis, then that means that the original function was increasing or had a positive slope. Okay, and if you're below the x-axis, that means decreasing. This is for the graph of any graph of any type of function for f prime. If you're below, then you had a negative slope, which means you were decreasing on your relation. So on f of x, okay, f of x was increasing. F of x is decreasing. So when the graph of f prime of x has stuff below the x-axis, we know that f of x is decreasing. When f prime has plots that are above the x-axis, we know f of x is increasing. So coming back over here, you would thus conclude that plot A, okay, which is steeper than plot C. Plot A seems to have a slope. I was trying to compare it. It looks almost 1-to-1, but it's actually a little bit bigger. You can see that it doesn't quite. This looks to be almost -1, and it's obviously 1 and 1 would be here. So it's steeper than that because that would be lower if you started from there. So 1.5 sounds reasonable. So I'm going to pair big A with little a. I'm now going to move on to the graph of C. C is the other increasing function, which means it has to be plot B. So big letter C goes with B. And I'm now going to look at the two decreasing ones. So we have D here, which is very steep. It's going on a steep incline, and B is less steep. So if these are the graphs of the slopes of these guys, which any derivative is, then we know that D, and these are linear, so that makes it easy because these will be horizontal lines because it's linear. because it's a constant rate of change or a constant slope everywhere along it. Just look here, this looks to be about a -2 slope, because you're up here at like you're up here at 2, and then you drop down 2 and go over 1 to get right to there. So big D goes with little letter d. And likewise, just making sure the recorder's working. And likewise, we can see B is a little less steep. It seems to be 1/2. And you can see it right here, 1 down and 2 over. And so that is 1/2 down there, meaning that this is a horizontal line of y equals 1/2. And that represents the slope at any point along the function b. And that's kind of obvious because in this case it's constant, but guess what? These will become curved, and then these will be curved as well. And you'll be able to match them together even when they're curved. Okay, so what other takeaways did we learn? First of all, the answer to, so B goes with little c. So the answers to 16 are right there. Go back, pause that video, listen carefully to what I'm saying, and you'll get a better sense. Make a little, put a graph on a nice page and just talk about, maybe entitle it something like properties of f and f prime, and even f double prime, the derivative of the derivative, which will come up soon enough, okay? Or something like that. That's enough. Properties of, plots. Okay, and start building up a set of patterns and relationships you see. So the other pattern that you learned that you may not want to put on the plot itself, but you put on the page of these notes, okay, which is a very important pattern that we learned, is that the f prime of x of a linear function is a constant. And that makes sense, right? Because if we take y equals 4x or something of that nature, y equals 4x has a constant slope. Okay, it always goes up in a 4-to-1 ratio. So the rise over the run is 4-to-1. Obviously this is grossly not to scale, so forgive this ugly plot. But you can see right there that whatever that slope is, if I get rid of that x, then y equals 4 will actually be f prime. And so a linear function results in a constant derivative function. Okay, so start thinking about what that would mean for x to the second, x to the third. What would their derivatives be? You might surmise by pattern that they do the same thing this one does. If this one goes down a degree, maybe these go down a degree. Okay, so keep all that in mind, but we've answered 16 and we're now going to pivot over to number 18. Alright, let's go ahead and get started on 18. First thing that it's easy to forget to do is to read the instructions and to take a deep breath, calm down, and make sure to understand what we're being asked to do. So sketching derivatives. Reproduce the graph of f and then sketch a graph of f prime on the same axes. Alright, let's go ahead and take a minute, pause the video, sketch this out on your own graph paper or make a little coordinate plane with enough accuracy and get this sketched in. And we'll come right back. I'll do the same thing. Alright, so I have mine. Hopefully you have yours. Let's zoom in here a little bit. And in order to get to plot the derivative of a linear function, we just went over the pattern that f prime of linear functions is equal to a constant c. So, and that constant c is just the slope of the original. So if this is a plot of f of x, I just need to get the slope of this branch. Did I make like a quadruple M there? Sorry. And the slope of this branch, and I should be good to go. So I'm going to go ahead and do that here for this first branch. So it's 5 minus 0, and then it's 1 minus negative 1/5. That's going to equal 5 over, let's see, that's going to be 1 plus 1.5, which is going to be 2.5. And so that's going to equal a slope of 2. And so we have a slope of 2 here. And so that means from this point and they said to plot it on the same coordinate. We're going to have a slope of 2. That means we're going to have a line coming here like this. And then right here it turns out, okay, that you guys need to memorize a rule. It turns out that the limit of the difference quotient at a sharp corner, I'm not talking about the two-sided limit. The two-sided limit here at x equals 1, we all agree is 1, 2, 3, 4, 5, right? But the corner, when you do this limit, when you do the limit as h approaches 0 of f of x plus h minus f of x and x plus h minus x, and you do this for both sides, and you do, I think in both cases you get undefined. In both cases you end up dividing by 0 when you do that at the sharp corner, and so therefore it's undefined. And if the slope is undefined at the corner, and I believe it's because the two-sided limits differ. So I believe, and you get like positive infinity here and negative infinity here when you do it. I wish we had time to do it. It's a great exercise. But what you guys need to remember is that sharp corners, okay, are not differentiable. And so likewise here, when we go down, let's get the slope on this guy too. 2 minus 5 and 4 minus 1 equals negative 3 over 3, which equals negative 1. So likewise this guy, which starts here, is also undefined. And then we go out to the point 4 along negative 1. Obviously that's, I'm emphasizing it with the size of that dot. And these two guys, okay, so that guy, this guy right here, and this guy right here are the plot of the piecewise function f of x, which is these two branches, and it's a piecewise function f prime of x. And that's what we have here when we do number 18. Okay, so we found the slope of each branch. You could also just do it visually if you wanted. I use the points because I'm plotting it myself and it's kind of fugly. And then just remember, one of the takeaways is you have to put a hole. These are holes. And they're holes because when you do the limit from each direction, you get undefined on the left and you get undefined on the right. One's undefined positive infinity, one's undefined negative infinity. Not only do those not equal each other, but they're not defined themselves. And that's because you're not doing this, okay? This guy is not equal to this, which is the limit at x approaching 1 of f of x. Don't confuse those. They're different things. These are different. Very, very different. This one's undefined. This one's certainly defined. They're converging on the 0.5. This one is about what the slopes are of these guys. Okay? And another way to think about it is, well, obviously constant slopes up to this point that are one thing, and constant slopes up to this point that are a different thing can't both be the same thing at the same point. So there's just kind of a natural logic to it as well. At any rate, here's how we want to start seeing that relationship. This guy has a slope of 2, so it's at a height of 2. This guy has a slope of -1, so it's at a height of -1. They're both linear and constant, so both of these are horizontal lines and constant functions. This one's y equals -1, given the domain restrictions, I'll just put dr, and this one is y equals 2, given the domain restrictions. All right, let's take a mosey on over and look at 50. All right, so I went ahead and plotted it. I forgot to pause the video there. So awkward moment, probably hear me breathing, cleaning my throat there while I was plotting this and focusing. So apologies. But as I do encourage you, and I do a lot of pausing here so you might say, oh, Jesus, he talks so much. I mean, are you serious? You do a lot of pausing? I do a lot of pausing. I want, the intention here is that you watch these very carefully, engage with me here, listen. It is unfortunate that you can't ask questions. We'll get back to that next week. But please watch these carefully, list your questions, write down questions when you have them, write down timestamps of the videos, and by all means, engage with me after the fact. But anyways, we have the plot of 50 here. And the instructions say to reproduce the graph of f. So that means this is a graph of x. It also labels it right here. This is f. And then plot a graph of f prime on the same axes. So we're going to do exactly what it says. And so you have that sketched. And then the next thing to do is to begin thinking about what are the slopes at the various instances here, and to kind of get a sense of what happens overall first, and then develop some new patterns, because now we don't have a linear function. We have a curve, okay? It looks to be like an x to the, it's like some type of x to the third or 1/3, but we don't need to speculate. But the problem is now is that unlike the linear function where it was just easy, we just, if we had a linear function, right, like 1, we could just write a slope of 1. It was super easy. Done. Now I have f and f prime on the same graph, right? But here, all these slopes are changing, so we have to think a little bit more richly about what we might expect for the graph of f prime given that information. So here's how we do that. Begin by thinking, what does the overall pattern seem to do? And it seems that this is getting successively flatter, and that this is getting successively flatter. And I base that on the fact that right about here seems to be its steepest moment. Okay, and somewhere in here it changes, okay, to where the slopes seem to be getting bigger as we go up this way. That's a relatively flat slope. Then they hit a maximum slope here. By the way, that's called the point of inflection. Okay. So they hit a max, and then they change. And the reason it's called a point of inflection is because they hit the max, and then they start to decrease. The slopes get smaller. And then the other thing I notice is like the first pattern I said is that the slopes seem to continually taper off. Continually taper off. And continually taper off means that they're approximately 0. They're going to get closer and closer to 0. And they're going to get closer to 0 over here as well. Okay, so they're going to get closer and closer to 0 everywhere. And the next thing you want to notice is that the entire graph is increasing. Entirety of f is increasing. Okay? I don't mean the changes in the slope on f, which is what I was talking about here. Here the slope, or the derivative of f, goes from smaller to bigger, and here they go from the biggest they get down to smaller again. What I mean is that the entirety of f goes upwards, that every one of these slopes, all slopes, are positive. So that means slopes are close to 0 over here. Okay, everything's smooth and continuous. I'm going to make a smooth line. They seem to be getting to a height of 1. That seems to be like 1 to 1, right? Doesn't that seem to be like a y equals x function slope? Seems like what it looks to me, and that's kind of how it looks in the book. And so we seem to be going up to a slope of 1, and then we go down in exactly the same way that we came up. Like, this is a mirror image of this. If I could like flip this over and then sandwich it that way, like if I could flip this graph around this way and then flip that around over to here, they would be the same exact line. So that means the slopes go down in the same way that they came up. And so that means it would just taper off like this. So we have a graph that goes like this and then like this. And this would be your f prime of x. Now, of course, when we look at the solutions manual, they do it all nice and pretty. I'll go ahead and show you here because it is kind of pretty, and we have no way of guessing what these functions are. So, well, we could guess something similar. Let's do that too, but just show you that briefly. And then let's pull up Desmos, and let's go ahead and plot x cubed. X cubed should be something roughly similar. And then let's plot 3x squared, and you'll learn why it's 3x squared soon if you don't yet know that. And oh, I guess no, it's not x. Yeah, it's 1/3. You know what? That's too much for today. We don't want to derail ourselves that much. Sorry. Yeah, it's not an x to the third function. It's a x to the 1/3 function. Let me just show you that it's one of those. And yeah. Oh, I need to turn it back on. Yeah, it's one of those. So let me go ahead and actually do that. Give me 1 second. Let me get it all queued up. Well, fun exercise, but you can see that it's almost similar. But the problem is instead of peaking at a slope here of 1, x to the 1/3 has a horizontal tangent here, and a horizontal tangent or a place where it goes completely vertical at an instant is non-differentiable. So actually these slopes increase to infinity this way, then become non-differentiable there, and then go from infinitely increasing downwards to approximating 0. So the approximating 0 part is really similar between our graphs, but right here in the middle. So who knows what this is? This must be something slightly different. Again, I'll go ahead and show you what the book did. And yeah, you can see it's different. It's not completely vertical here. And so that's why this one tapers off like that. But if we twist this and tweak it and make this inner part here more vertical, this bump here will continue to rise up. And if we make it completely vertical, it'll turn into asymptotes. So it's just some cool patterns to see. So just helping to make sure we're getting a full discussion of how we get these graphs and how we develop these sketches, and not just rushing through it. So what are some key takeaways that we noticed here? We noticed that the whole graph was increasing, and so if the whole graph is, if graph of f is increasing, that means f prime will be above x-axis. So that was one pattern we noticed. We noticed that the slope, there was a type of symmetry to how the slopes increased here and the slopes decreased here, and that the slopes went from increasing to decreasing, and that there was a point of inflection where those changed. Let me see if I want to talk about any more on that before we move on. And I guess the last thing I want to say is that if you notice on original f, so this is original f here, okay, original f, the shape is upwards, and that shape there is called concave up. And so when f is concave up, we notice that f prime, this graph here, is increasing. And that makes sense because we talked about how the slope down here is lower and the slope here is higher. That's a lower value, that's a higher value. And so when f prime increases, okay, that means that f was concave up. And likewise, when f prime decreases, so f prime is decreasing here, that means that the bowl shape is downwards. So that's concave up, this is called concave down. So we notice that f prime is decreasing when we're concave down on f. And so I talked a little bit in the last problem about developing a whole page on properties of f, f prime, and f double prime. We don't typically go farther than that for spot graphical analysis, but you want to add these to your lists. And then again, just the terminology. It's totally understood that you can use POI to represent the point of inflection. And this is where concavity switches. It means there was a concavity change. Okay? Incidentally, that also means that if you make an F prime chart and you have some point X here, and on this side it's negative and on this side it's positive, it will mean that the concavity switched in a certain direction. So in our case above, we have positive, negative. Okay? So eventually we'll be able to leverage different tests to talk about concavity, and these are going to be called sign charts. But we'll get into that later. Just make sure to add these to your list. Consider 50 done, and we're going to move on to the next one. Okay, so next up we have problem 60. 60 says to sketch this, sketch f prime, so let's go ahead and do that. And f prime is a slope of 2. So this is y equals 2, which is f prime. And that's what we have. We'll go ahead and put a 2 there. Put a 3, 4, 5. We'll mark 5 off, and maybe 3, 4, 5 down, something like that. Keep the same scale factor here. That should be enough to get us started. We'll go ahead and zoom in a bit. And so they now said to sketch 3 possibilities of f. First, why did they say 3 possibilities of f? Well, what we don't know is we know that we have mx plus b, right? Is our parent form of a linear function. And we know that because this is a constant, okay, if the slope is a constant, we already talked about how that means that f of x must be linear. Okay? But when you think about it, mx plus b, b's could be 0, b could be negative some number, it could be positive some number, where a could be any real integer. If it's 0, then that would mean that it could be, oops, it's 2, sorry. Yeah, I did the tilt wrong. All that nice drawing to screw up your graph. Okay, so there is a slope of 2 to 1. Okay, so if the original function, the primitive, this is the derivative, if f of x was 2x plus 0, then that's a possibility. But what about f of x equals 2x plus 3 and f of x equals 2x minus 3? Do these work, and why do they work? So ask yourselves, regarding these two functions, what are the slopes of each? Or I could say it a different way, what's the rate of change of each of these functions? And does the 3 or the negative 3 have an impact on it? And the answer is it doesn't. The slope or rate of change of these functions is still 2, which means f prime is still going to be 2, even in these cases. And if you think about why that might be, now that you know what derivatives are, well, just think of the graph of y equals 3. Y equals 3 is a horizontal line. Sorry, I'm looking while drawing at the same time. So here's good old y equals 3, right? And it's completely flat, it's horizontal, which means the rate of change is nothing. It's never changing any heights or changing any slopes. It has a constant slope. So the derivative of this is 0, and the derivative of this is 0. So these guys have f prime equal to 0. And that's why they have no impact on what the answer is. Which means that either of these could be an answer to this question, meaning that we could have y equals 2x plus 3, so we could have this same line, same slope, trying to draw it as perfectly as possible. Okay, so these are the same slope, and it could go through 3, or it could be this one, 1, 2, 3, negative 3. And just these all have same slope. Okay, my drawing's not 100% perfect, but you get the idea. And it turns out you can make up whichever ones you want. You don't have to even use this one necessarily. It's the first one that comes to mind. If we don't know anything, we wonder if the starting point was 0, the initial condition, but we don't know, okay? So anything that you pick here, as long as it's a y equals 2x function, and you have 3 different numbers here, would be considered an acceptable answer for this problem, and then you need to include the plot and plot them all on the same piece of paper. And that's what's required for number 60. So hopefully that helps. Every one of these f of x's that I drew here could be described. This f prime here has a slope, has a height of 2. The height of the f prime, or the output of f prime, is a slope value, and that 2 represents the slope in the constant rate of change that all 3 of these linear functions have. Okay, so 60 is done, and I think that wraps up 3.2, and we're going to close that up. I guess I'll just say keep up the good work. Make sure that you're pausing the videos and doing on own. 2, make a list of questions and follow-ups. This includes if you see any mistakes. If you think I got onto a rant and I never caught a mistake and I carried it on, please bring that up and let me know. Of course, we're upset when we make mistakes, but that's not a big deal. And you will get Ninja Ducks for that. Okay, and Ninja Ducks is brutally stolen from someone who shall remain nameless here, but I brutally steal it and love it. Okay, and so make sure you're pausing the videos and doing on your own. Make sure you're making a list of questions. 3, remember that I have tutoring available in the evenings at different times. DM me. I am down here in Albuquerque all week filling in at this conference. It was a little unexpected, as I told you on the course announcements. 4, you guys, you need to read the course announcements. I'm not talking to just one of you. Okay, there's a few of you in here. Things happen in college classes. Okay, I'm traveling this week. I'm not going to leave you hanging, so I'm making large videos with lots of material, lots of learning, lots of me talking you through how to do the problems, lots of me talking you through what's going on, and then there's usually a problem or 2 left over for you to do, just as if we had an in-person class. The only difference is you need to make a list of questions and follow-ups because we can't field those questions right now. So, did I say course assignments? Course announcements. But the last thing is what we're missing is a lot of you are failing to read course announcements. This is super important. This, okay, and modules. A, B, modules. These are like the 2 sacred things for my class for Canvas. You need to check these every 24 hours. I can tell because Canvas, the domain Zoom that we have, emails me when people are coming to classes. So, if I sent out an announcement 48 hours ago, 72 hours ago that we're not having class, we're doing this, I just get concerned. I'm not upset at anybody. I'm not upset at you guys. I love you guys. You know that. What I mean is like you might want to check it a little sooner because you need to be on a quicker pace overall for everything. So I have, 2 or 3 different the first time than the other time. But I noticed a pattern where I can tell from timestamps, joining meetings on Zoom, and different things that I see on my logs that we're not checking course announcements enough. And yes, I apologize. This came up a little unexpected. We had somebody who was going to man the booth. A committee fell through. And then we had Juneteenth, which is awesome that we're honoring that and taking that off, but it did impact our schedule because I'm not going to break a federal or state holiday, especially not one that important. So these things happen. So you have to check course announcements out when these things happen. I could also be that teacher that just says, yeah, we're not going to have class this week because I'm traveling, and give you like a packet or something. I'm not going to do that. We're making videos. But where do I tell you that information? In course announcements. So you guys know I have your back. Okay, I want you to check course announcements better. Most of you are checking modules right. Okay, this ends. Chapter 3.2 is now over. And we're going to move on to the other videos, the other topics that we need to do. And you're going to have 2 more videos as we're going to do some 3.3 problems, some 3.4 problems. And we're also going to go over the derivative worksheet, okay? And we'll go from there. So hang in there. Remember to do all these things. Reach out to me. Don't be a stranger. Talk to me. Communicate with me and let me know what's going on. I'm here to help you, okay? And we will resume synchronous online instruction, remote style, next week. And for this week, I'm making these videos, and avail yourselves of them. And that's it. My pep talk is over. You know I love you guys. I'll just end on this, that we got this. All right, we got this. Let's go. All right, guys, we'll talk to you on the next video.